This is the 6th episode of the PEC GPS series, and on this video we'll go through the concepts of position error correction data reduction process for the GPS turn regression method. Let's dive in!
3, 2, 1, top.
3, 2, 1, half, the Flight Test Engineering channel.
In the 2000s, GPS was becoming a big thing, and its affordability was increasing fast. And we, as flight test engineers that we are, we were starting to have all sorts of ideas on how to use them. At the same time, our VSM was being implemented around the world, and the OEMs and operators were having quite some challenges for showing compliance with the airspace. And at the time, the typical setup was to install a trailing cone on a production aircraft, go for some flights using the trailing cone as a truth source, and then try to statistically prove that your fleet is or was sound, which was not at all trivial. And also, since our VSM space is quite high, the flights needed to be done up there at higher altitudes. In the later part of the 2000s, while still working at Grub, our colleague Al Lawless had this great and novel idea of using one of the most precise measurements that the GPS unit can give you, which is ground speed, instead of position, to obtain the static source error correction. And he proposed to do that in a completely different way than the GPS had been used so far. You see, GPS derives ground speed from the Doppler shifts in the satellite signals, which results in a much more precise value than trying to compute position. In this method, instead of flying 3 or 4 different headings, as we saw for the cloverleaf method, where airspeed variation between test points cause significant error, and also if the wind changes, that breaks a fundamental assumption of the method, why not go for a continuous measurement of ground speed and ground track and derive a much more statistically robust calibration? So the Orbis method came to life. The idea is to fly a constant bank, constant altitude, constant airspeed turn, and collect GPS ground speed, ground track, as well as the ship's outside air temperature, indicated airspeed and heading. And if we plot the ground speeds east versus north components, we get a circle, thus Orbis, but offset from the center by the wind. Now, there are many ways to fit a circle to the data. There is the original 6 steps method that Al derived back then. There's the CASA method borrowed from computer graphics. There's the geometric method. There's the inversion method. But we'll focus here on the turn regression method, which formulates the problem as a general regression model. Let's look at how this is done. We are running FlightGear with an Airbus 320neo already started up and warm. We'll be taking off from Innsbruck to 10,000 feet, and I will set up an initial heading to north, so it will be easy to track our progress during each test point. Of course, this is completely arbitrary, and let me speed up the footage here until we are about to start the test point. To execute the test points, I'll call upon Ms. Honeywell here, and she'll take control with an alt hold, auto throttle, or auto thrust as Airbus likes to call it. And for lateral mode, we'll use good old heading. So after we are stable on the speed we want, and in this case we're starting off with 175 indicated, we just keep changing the heading bug until we complete one full orbit. The idea is to repeat the process at different speeds and altitudes. And here you can see I'm doing test point number 2 at 250 indicated, and so forth. On this flight, I got data for these 2 test points plus VMO 350 indicated at 10,000 feet. And higher up at 31,000, I got points for 172 indicated, the slowest I could keep the autopilot auto throttle on. And then Mach 0.6-ish, and then Mach 0.82, which is the MMO for the 320. And now let's look at this data and see what we got. What we are looking at here is a tool that I built to slice big chunks of data that we typically get from flight test instrumentation. And let's load in the turn regression that we just did for the A320. So I'm going to select that and it imports it. Let me just zoom out a little bit to make it easier for us. So these are the parameters that we got in the file. And if we look, for example, at psi in degrees, we can see that we can detect the turns here. And how does the tool work? Well, this is the full flight data. And if we select this part, we can zoom in and determine when the turn starts and when the turn ends. So we can, make this more zoomed in and see that we have the turn here. And we can also plot indicated airspeed on the same graph here because the scales will match more or less. And we can see that we were right there at 175 knots-ish. Let me just reset this thing here, right? So when we are happy with this test point boundaries, we can say that this is the first test point and it was at 175 indicated and 10,000 feet, right? And we can save the slice, and now this slice is ready for us to do other things and load in our Python script later on. So let's go on and look at the second turn, the one that we did at 250, and you can see here that the boundaries are also pretty easy to spot. And down here, let me just zoom in a little bit more here, and you can see one detail here is that the turn in the beginning, it's not stable, so we need to discard this. So let's discard a little bit because we don't need the full 360. We can work with just a little bit less. So this is test point number 2 at 250, 10,000 feet, 250, right? And we saved our second time slice here. The third one's going to be at VMO. And if I recall correctly, this is around 350. Okay, zooming in here. Yeah, 350 is the number. So right there, test point number 3. And this is 350 at 10,000 feet. How do we know it's 10,000 feet? Well, let's check. Let's look at altitude in feet. There you go, 10,000 feet. So the next test points that I did at 31,000 feet. So let's keep going with our psi. We don't need altitude anymore, and we go with indicated airspeed. And you can see here that the trace for airspeed is much more noisier. It's because I added turbulence to these test points to make it more fun, let's say. And here's the other test point. This is at, I think, MMO, all right? So there you go. That's the test point limits, 320-ish knots. So this is going to be MMO, Mach 0.82. And this is 31,000 feet, 31,000 feet. And this is test point number 4. You can see that the time to turn is much longer here. Well, because you're faster and your turn radius is longer. And also because the Airbus autopilot limits your bank angle according to speed and altitude, right? So let's keep going here and get the other test point. This is Mach 0.6. All right, so right there. Okay, so Mach 0.6-ish, 31,000 feet, test point number 5, save slice. And the last one, you can see that I struggled here to do the turn. I tried once, tried twice, 3 times, 4 times here. And what happens is that I was trying to go slower and slower, but then as you stabilize going straight and as you try to turn, the auto throttle and autopilot was kicking out because I was hitting off a floor. So I had to bump up the speed a little bit so that we could complete the turn, right? So this is one turn here, and the speed was what, 175, 172 if I recall. Yep. So this is 172 indicated and 31,000 feet, and this is going to be test point number 6. But now, what other functionalities can we have here? Well, in my analysis tab, what you can do is you can select your test point. So let's say test point number 5. Let's look at indicated airspeed, and you can see, for example, that it has a lot of noise, of course. Well, not a lot, because we're talking about 2 knots here, right? But anyhow, you can apply a filter, for example, a low pass filter to this signal here. So I'm going to apply a filter, and when I apply, I create a new parameter, indicated airspeed filtered. And if we look at this in our analysis, I can look at both indicated airspeed and filtered indicated airspeed, and you can see that the filter is a low pass filter. It will smooth out the imperfections here. Also, I can chop off the ends here, right? I can fine tune the ends, but I'm not going to do that and trim the current slices. I can also create strip charts, but I'm not going to show this in many details, but I select a test point and I select parameters, rudder, for example, and I can click here and get the strip charts that I can paste on my report, for example. But the important part here is that I can save the slices that we selected, and I'm going to save all parameters here to disk. And now I can download this zip file, which contains all of the data that we have available already sliced for these test points, which is very convenient and will help us in the next step, which is when we do our day reduction routine in Python. Okay, so let's start with our wind triangle here. We have the airplane going north roughly here, and we have the indicated true airspeed vector plus whatever delta VT that we don't know that we're going to find out. We have the wind blowing, and we have the ground speed and ground track. And of course, our indicated plus the error is going to be our true airspeed. So let's use a trick here on our Jupyter notebook that we can create another view here for this part of the cell and put it on the side. So to do this, I need to undo my simple here, and I right click on the top and I say new view for notebook, and it creates a new view here, right? So we're going to leave our wind triangle here on this side. So let's keep going here on the GPS. So we know that we can decompose each of the vectors in the east and north directions. Therefore, we're going to have for the ground speed, we're going to have a east and north, and the components are going to be the ground speed times the sine of my ground track and times cosine of my ground track to give the east and north components. That's easy enough. And the calibrated true airspeed is going to be its indicated value plus the error, as we show here, our VTI plus delta VT, right? VTI plus delta VT vectors, which we can also decompose into north and east components by using the cosine of our psi test, right, for the north, and the sine of our psi test for the east components. So from the wind triangle, we can then write the ground speed as our indicated true airspeed plus the delta VT plus the wind, right? So we're doing this vector sum here, indicated plus whatever error we have plus the wind is going to give our ground speed. And we can rearrange this to write that our indicated plus error, which is this vector, is going to be ground minus wind, right? Now we can expand, and we can move this a little bit. We can expand this vector equation into the north and east components by writing our true indicated. It's going to be the cosine of our psi test as we had up here, plus whatever error we had times the cosine of our psi test as well to get the component is going to be whatever component we have on ground speed, which is VG times cosine of our ground track, plus whatever component we have for the wind in the north direction. Same thing for the east portion. And now we can rearrange these equations to write everything wind on the side, VWN, plus our error times cosine psi test equals our ground speed, which we know, minus our indicated true airspeed, which we know. So it's unknowns equals something that we know. Same thing for the east component. And now we can write this in matrix form. Let me see if we can rearrange this farther to have 1 times V wind north plus 0 times V wind at east times cosine psi test times delta V, which is this equation here, equals VG cosine sigma ground minus VTI times cosine psi test. And same idea for our east component, right, 0, 1. But now let's think a little bit. This is true for one wind triangle that we fly at one test point. And when we are doing this regression method, we're going to collect many points as we go. As a matter of fact, every second or if we're recording data at 1 hertz, every second we're going to have a data point. Every second we're going to have a triangle like this. So actually we can stack the measurements up on the same equation, given that our wind is considered constant, so VWN and VW east are constants along each measurements. That's a fundamental assumption from the method. And also our error is going to be constant, our delta VT. So we have many equations, many wind triangles for the same 3 quantities that we don't know. And finally, we can do a last adjustment here, which is instead of having 1, 0, 0, 1, 1, 0, 0, 1, we can rearrange the order and have them more easily programmable by having all 1s here and all 0s and vice versa, meaning that we have all the cosines stacked up here and all the sines stacked up here to have the matrix equation in this form. So we can now say that the matrix equation is going to be something like A times X, which we don't know, equals C. Okay? You are seeing these spaces here because this is where we're going to insert our code later on the next part of this video. And the concept of solving the system is that we have the equation, the matrix equation, and we can rewrite it by saying that C minus AX equals 0. So this is telling us that we have a solution, we should have a solution for X that gives 0 as a result. But we don't have a unique solution here because we have many test points and we might have a few X's that satisfy this. So we need to pick a good solution. So what is a good solution? Well, it's perhaps one that minimizes the error, meaning that C minus AX as close as possible to 0, which is what we want. So we can create a functional, we can call it J, which is the typical name for that we can minimize. And we can define this functional as the square of the error. You know where we're going here. We're going for the least squares. So we can define J as being our error squared. Now, we know these are matrices, so we have to expand this. We can write C minus AX transpose times C minus AX. And then we can pass the transpose operator into the parentheses, and so we have C transpose minus X transpose A transpose times C minus AX. And now we can group like terms. So we have C transpose times C minus X transpose A transpose times C, that's this multiplication here, minus C transpose AX plus X transpose A transpose AX. And to minimize this functional, meaning that we're trying to minimize the error, take the partial derivative with respect to X and set it to 0. Okay, so taking the partial derivative of this equation here with respect to X, we're going to have 0 minus C transpose A minus C transpose A plus 2X transpose A transpose A. And we know this is going to be equals to 0 because we're setting that del J del X equals 0. So we can eliminate, or we can sum the like terms here, and then we're going to have this equation. 0 equals minus 2 C transpose A plus 2 X transpose A transpose A. We can cross out the 2's here and pass this term to the other side, and we have X transpose A equals C transpose A. And now we can take the transpose of the whole equation, and we're going to have A transpose A, X equals A transpose C. Next step is going to be that we're going to pre-multiply both sides by the inverse of A transpose A. So A transpose A inverse times A transpose A X equals A transpose A inverse times A transpose C. This is the identity matrix. So we end up with X alone on this side. So we have X equals A transpose A inverse A transpose C. And this term here, this is called the pseudo inverse, okay, which we can calculate. So if we solve this, we're going to end up with X equals V wind north, V wind east, and our delta VT, okay, which minimizes the functional J as we formulated following the least squares concept. And then we can go ahead and find the wind speed by doing our Pythagoras, and then find the wind direction as well, since we have already the two components. Okay. I hope this video helped you understand the math behind the GPS turn regression method for position error correction, and I will join you in the next video where we're going to code all this in Python.